Or not so little? Okay. It's kind of an example of a run-on sentence, which, you know, given that you're working on your writing, maybe we can go through. It's a statement made by Isaac Newton when he was looking back on his youth. And this is after he's master of the mint, and he's more or less winning the calculus wars with Leibniz. And so he's looking back at what happened at a time in his life when he was forced to go home from the university in Cambridge because the plague had arrived in England. And so the university was disbanded for a couple of years. And so he says, in the beginning of the year 1665, I found the method of approximating series and the rule for reducing any dignity of any binomial into such a series. The same year in May, I found the method of tangents of Gregory and Slossius, and in November had the direct method of fluxions. And the next year in January had the theory of colors. And in May following, I had entrance into ye inverse method of fluxions. What is ye inverse method of fluxions? That's integration, right? So fluxions would be derivatives or differentiation, and the opposite would be integration. And the same year I began to think of gravity extending into ye orb of the moon, and having found out how to estimate the force with which a globe revolving within a sphere presses the surface of the sphere, from Kepler's rule of the periodical times of the planets being in sesquialterate proportion. Well, you don't use that term all the time? Yep. Okay, good. The center of their orbs, I deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve, and thereby comparing the force requisite to keep the moon in her orb with the force of gravity at the surface of the earth, and found them answer pretty nearly. Is that the end of a sentence? Well, okay. All this was in the 2 plague years of 1665 to 1666, for in those days I was in the prime of my age for invention and minded mathematics and philosophy more than at any time since. I believe all the misspellings are the authentic originals for your delectation. Okay, time for a little bit of a translation. So clearly the numerologists understand that this miracle year came about because of the Roman numerals. 1666, what's weird about that?
There's one of each.
One of each of the Roman numerals, so clearly it was destiny. And in that time, having absorbed the mathematics of the ancients and of Descartes, Newton was thinking about both mathematics and physics in describing motion, and had therefore the need to invent the differential and integral calculus. He came up with an inverse square law of gravitation, so he claims, and a very fundamental discovery in optics and the laws of motion that we have been elaborating. That's a pretty good haul for about a year's work. So he is much celebrated. And what was this law of universal gravitation? If I have a mass m1 here and a mass m2 there, we've seen by extrapolation from the experiments that we were considering in the bubble that the force of one on the other is equal and opposite to the force of the other on one. And the form of this force that's directed along the line between the two objects is proportional to the product of each mass and inversely proportional to the square of the distance that separates them. There's a problem, though. The Earth doesn't look like a little point. It's quite extended. So Newton worried a lot about, well, what if you have a spherical distribution of mass? How does that behave? So each little part of mass, imagine I have an extended body. Each part of mass here is going to exert a force on this object in the direction of the line connecting this mass to that little bit of the big mass. But there's another little bit over here, and so I have a line there. And I have to add up all these contributions, and it's not obvious, is it, that that should simplify. So he had to do a little work. Fortunately, in the Principia Mathematica, he enunciates for us Theorem 30, that a mass inside a uniform spherical shell of mass experiences no gravitational force from the shell. So imagine I have a uniform thin shell of mass. If I put, well, let me put the mass first right at the center. Is it clear if I put it at the center that there should be no net force on the mass? Why? What's the argument? Yeah. Charlotte?
All the forces are going to cancel each other out.
Yeah, pairwise, right?
Yeah.
Yeah, so for every, that's not very well in the center, but let's pretend that's better in the center. So for every little bit of attraction out that way to this little bit of the shell, on the opposite side, there's a corresponding companion bit, and it is exerting exactly the same force but opposite. At least that's true if we're at the center. But what Newton is claiming is something even more general, that it doesn't matter where you put it, even down here, that it will feel no force. Is someone able to make an argument why that might make sense? Yeah, Thor?
I'm able to make an argument against it.
Go ahead.
We're underground right now, and we feel gravity. So why?
We're underground now, we feel gravity, so why? Ah, that's a different circumstance because we're not worrying about a thin shell, but what the application of this argument that would be relevant as you go down inside the Earth is that the mass of the Earth that's farther away from the center in that shell than you are doesn't count. It doesn't contribute to the gravitational force on you. That's what this is claiming. It's a shell. It's a thin shell. Yeah?
I'm going to take a stab at this.
Sure.
Because, so if you're at that point that's near the bottom,
Yeah.
there's more mass above you than there is below you, well, defining above as up. But the mass above you is also farther away, and so we apply F is proportional to m over r squared. It, like, the increased mass cancels out the increased distance.
So the argument relies very carefully on the fact that the force falls off like 1 over distance squared. If this point is close over here, let me just consider the same little bit of angle, which I've drawn grossly large, and I want you to imagine instead that it's small. But for every little bit of wedge, there's some mass here, and there's a lot more mass there. And in fact, if I were to put R here and capital R there, the ratio of the masses would be like the ratio of the areas. Each little bit would look approximately like a circle, and the radius of the circle would depend on the angle and the distance away from this point. So the area here compared to the area there would be smaller by a factor of this r over that r squared. If you like, it looks a little bit like similar triangles, except that we have to imagine patches of circular patches of area. Yeah?
Doesn't this follow from one of Kepler's laws?
Well,
I mean,
No. No, I don't believe so. and so he's asking whether this follows from Kepler's laws. And I think in an important way, that's irrelevant because Kepler's laws find their explanation more deeply in the Newtonian formulation. But I don't believe that the shell is deducible directly from Kepler's laws, and nor was it known to Kepler. So the area down here over the area up there should go like r squared over r squared. And yet the force, so the area goes that way, the mass is proportional to the area. And so do you see how if the force is proportional to the mass over the distance squared, the mass goes up like the distance squared, and therefore the force on either side will just exactly balance. So Newton had to show that, and then we could say, aha, that's the first half. The second half is that outside a shell, it's as though all the mass of the shell were concentrated at the center. So if you're inside, it disappears. If you're outside, you can pretend that all the mass in the shell is just located at the central point. So that simplifies things a lot. Yes?
So what if you were on the outside of the shell being pulled towards the center of the shell had a hole through it?
Yes.
Would you fall through the hole and then just keep going with it?
So he asks, what if we put a hole in the shell and drop me in? Would that mean there's no quiz tomorrow? Wait, no, that's not what you asked. So if we have a hole there, and we put a hapless astronaut here, is the astronaut attracted to the shell?
Yes.
Okay, so the force on the astronaut from this shell, providing I can neglect this little bit of mass that's gone, is as though all the mass of the shell were concentrated here. So does the astronaut fall? Yes. Falls towards the shell. And then what happens as soon as the astronaut has crossed inside? So now moves at constant velocity because there's no more force caused by the shell.
Well, he's half of his body above the shell and half of it below. You have like his legs and still attracted to the shell.
Yep. I'm not recommending that you build such a structure, but that's what goes on. Okay, so these are very important theorems that allow him to apply gravity, the law of universal gravitation, to all sorts of situations. The first of which, and that we're very much familiar with, is that gravity is approximately uniform near the surface of the Earth. So there is a value with which we're all acquainted, about 9.8 meters per second squared.